what are we going to do with this, right? We're going to use it for impacts, right? You could use it from what we were doing right there, but I just want to use it for impacts here, right? Just to keep it with the theme that we were doing for particles, okay? All right, so some key concepts here to talk about. Okay. When we have impacts of rigid bodies, we have to be worried or be considerate of translation and rotation. Components. Right. Forces and moments. Right. And then that's tied directly to linear momentum and angular momentum. Right? We have to be concerned with both of those things, right? Because you can have conservation of linear momentum and conservation of angular momentum. Might have to use both of those to solve, right? Right? I'm going to say this again. Mechanical energy is not conserved across a collision. Right? It is not conserved. Please do not do energy before and energy afterwards, right? It's an easy one to grade when I see that. Internal force pairs have no net impulse. Right, we did that in and kind of proved that or discussed that in particles, where if you have, an object strikes one object and that object strikes the original object back, right? So the projectile will hit the object and they have internal and they're equal and opposite, so they cancel each other out, so they have no net. They have effects on each other, but they don't have, on the whole system, they do not have an effect. Okay? For simplicity, it is often convenient to pick moments about fixed points rather than mass centers, if you have the option. If you choose mass center, you need to track movement of the mass center. Uh-oh. Oh, dang it. Why? Track. Okay. There's some key notes there as we go into this thing. Right, I'll give you a procedure. And do the same thing we've done before. We start out with the free body diagram. F, B, D. We are gonna look to see where MO equals 0, or the sum of the moments equals 0. If you find angular momentum is conserved about that point, you gotta go find it. Right. Also under this one, I put that underneath. Actually, I'm gonna put this, it's easy for me to do. See if angular momentum or linear momentum. Uh-oh. Yeah. What happened to my keyboard? Okay, I'm back to it. All right. Let's see if angular momentum or linear momentum is conserved. Okay. Look to see where the moments are equal to 0, then angular momentum is conserved around there. Find if sum of forces equals 0. If so, linear momentum is conserved. And then under this one too, I'm going to write appropriate equations for each case. Right. 3, kinematics is required. And then 4, solve. Note, problem will most likely have a work energy component. Okay. To make these a little bit more interesting, we're going to combine them with some work energies. Some tabs in there. Uh-oh. Technical difficulties today. All right. Cool? Yeah.
What's the lead for ML equals 0?
Oh, we. That is supposed to be aware. Okay. All right. The appropriate equations, just to kind of write them down here again. This is going to be where the moment is equal to 0. It's going to be HO1, HOA1 rather, because we have multiple objects. HOA1 plus HOB1 is equal to HOA2 plus HOB2. Right? That's the equation I'm referring to there. And then down here, linear momentum, MA-VA1 plus MB VB1 is equal to MA-VA2 plus MB-VB2. Right? Those are the appropriate equations that we're talking about. We'll start an example here. Give you a second to write that down. Okay. All right, this guy. All right, this bar is hanging down. There's a projectile, a particle that's going to come slamming into the side of this thing, right? And we are asked to find bar is at rest and has a mass of 5 kilograms. That is struck by a bullet B with a velocity of 400 meters per second at the angle shown. The mass of the bullet is 0.004 kilograms. The bullet strikes and embeds. Find omega of the bar and the bullet after impact. Okay, there's no work energy component of this. It's just like what's happening immediately after the impact, right? Because the momentum of this, right, is going to be imparted onto the momentum of this, and then the two stick together when they move, right? There's no real energy to discuss here, right? Let's do it. Okay, so let's follow our steps. Free body diagram. Ooh, 1, F, B, D. Okay, see what's happening there. We've got our object, isolated bar. We have acting on it. We have mass times gravity acting down. And gravity. We've got reactions. OX, OY. And then we've got right, the bullet, I guess the bar striking the bullet and the bullet striking the bar. Okay, that's what's happening. All right, so then that's everything that's in there, right? A free body diagram, kind of identify the forces that are acting on there. Uh-oh, I don't want to grab you, I want to grab you. Okay, so then the second step was you try to find to see if linear momentum or angular momentum is conserved, right? So is there any point on here where angular momentum should be conserved, where the moments are 0? Right here, right? This has, this has no moment arm, that has no moment arm, mass times gravity has no moment arm, and these guys are canceling each other out. So right there at that fixed point, that moment is equal to 0, right? So angular momentum should be conserved about that fixed point, right? It would not be conserved about this point down here, right? Because this would have a moment, because there could be an OX component to that, and that would have a moment there. But right here, angular momentum is 0, okay? So that's great. So that's, how about linear momentum? Would there be any linear momentum? Would linear momentum be conserved? No, right? Because we're going to have a reaction, OX and OY. Those are forces that are acting on this thing, right? And since there's forces there, then there is no linear momentum is not conserved. If those forces weren't there, the next example we're going to do, right, is this one where this thing is allowed to kind of slide back and forth or roll back and forth. In that case, there would be no reaction in the x direction to stop the linear momentum. In this case, this OX force, when this slams into it and this tries moving, there definitely will be a reaction force there that's not going to let linear momentum be conserved. It's going to hold it in place. So linear momentum is not conserved, but angular momentum is conserved. Angular momentum conserved about O, since no moments there. Linear momentum is not conserved. OX force. Okay? That's part of it. So then the equations that I get to write down, right, is I just have the angular momentum equation. I guess that's part of step 2, to be consistent here. I'm going to just be consistent. Check for angular momentum and linear momentum. Okay. Conservation, right? And then I'm going to move this down into that, because that's really step 2. All right, and then the appropriate equation we want is the angular momentum. Angular momentum, which tells us that HO, we'll call it bullet, B1 plus HO bar 1 is equal to HO B2 plus HO bar 2. Okay? So this thing isn't, the bar is just sitting at rest when that thing strikes it. So there is no initial angular momentum of that bar. Okay? So now at this point we'll expand it, right, to see what those, we haven't written down what the equations actually are, right? On the right-hand side, we've briefly discussed this, right? We said that this is going to be, well, let's get to that second. We'll go back here. Let's do the left-hand side first. HOB1. B1 is just a particle, right? This is just a particle, so it has no angular momentum about its own mass center. The only component it's going to have is that R cross MVG. All it's going to have is, go back to this one. It's only going to have, well, let me grab it. I'm going to borrow this. Uh-oh. Right, for the particle, right, it has no angular momentum about its own mass center, or I would be 0 for that, basically. It would be spinning, probably the bullet would be spinning, but it would be about different axes, but it also have a really small moment of inertia, so we're going to ignore the angular momentum about its own mass center, but we will have this, an R cross MVG term. We are going to have a moment of linear momentum, and this is what we did with particles too. When we talked linear momentum of particles, this is what it was. Right, just R cross MVG, okay? So this just becomes R, B is seen from O, crossed with MVB1, ooh, MB. You gotta keep track. I have multiple masses floating around, so this is MB, right? That's the angular momentum of the bullet. The bullet after the collision, same thing, RB is seen from O, crossed with MB times VB2. And then the last one is, we're going to do the angular momentum about a fixed point. So this is just going to be I the bar about O times omega bar. Okay. Be okay with that, right? I mean, just the particle stuff, that'd be the biggest kind of leap there. It's just what's happening with that bullet's just a particle. So it's just R cross MVG. It's R cross F, right? It's the moment of linear momentum. So it's just this component, right? And then this is the bullet after it strikes, because it's still there, right? It doesn't weigh much. We're going to learn later that we could probably ignore that component, but that's still there. And then we have this moment of inertia of the bar about O, because we're going to do it about the fixed point. That's where our momentum is conserved about, times omega bar. And what we're after here, by the way, is this omega bar, right? The problem statement says find omega, the bar, and bullet after the impact. So really we're after that omega bar. Okay? So at this point, we just start cranking stuff out. Negative 0.75 in the J. Right. That is our RB seen from O, crossed with the mass of the bullet, 0.004, times its velocity, it's 400. It has a direction associated with it, which is cosine 30 in the I minus sine 30 in the J, right? That's just the components of it, right? Because it's coming in at an angle, so you put it in there just like that. Only one of those is going to cause, with a cross product, it'll take care of the fact that one of those doesn't cause a moment. All right, keep going with it. Negative 0.75 in the J, crossed with 0.004 times VB2, the velocity afterwards, plus IO times omega bar in the K direction. IO, we didn't do our mass props, but in this case, it'll be ML squared all over 3, which ends up being equal to 5/3. Right? It's ML squared over 3 because we're doing the bar about its end, not the bar about its mass center. Okay? So there, we're like, oh yeah, we got it, right? We got it, we're done. Nope, we're not done, right? We got too many unknowns, right? We got, this side's fine, I know everything there, but I have VB and omega bar, right? I need to relate those two, right? Because again, this is the only equation I get. It's the only equation I got. I need to be able to relate those two. And they will be related to each other, right? Because after one's going to be stuck in there, right? It's going to be stuck in there, and then the two are going to rotate together. So the kinematics should tell us how those things are supposed to rotate together, right? So let's do kinematics. 3 minutes. We'll at least start this. Kinematics. VB2 is equal to VO, right? I know the velocity at point O is 0, so I'm going to start there. And plus omega bar crossed with RB is seen from O. Right? So I just taken a step. I'm taking a step from here down to where that bullet's at. Right? And I'm starting at VO because that's 0. Right? So let's just write out our stuff here. VB2 is equal to omega bar in the K direction. And I cross that with negative 0.75 in the J direction. And that equals 0.75 omega bar in the I direction. There's our relationship. That's what VB2 is equal to in terms of omega bar, right? Now I just take that and I substitute it in up above. So We're gonna finish. We're gonna get it. We're gonna get it. Let me just write it. Let's write it all out now. So now you take that and substitute up above. So 1.03 in the K is equal to 0.75 times 0.75 times 0.004 times omega bar in the K. That's the angular momentum of the projectile after the collision, plus 5/3 omega bar in the K. Okay, and then what we're after is omega bar. So now you just solve for omega bar. But one thing I wanted to point out before we do that is this. Look how small that number is going to be. 0.004 times 0.75 times 0.75. That is a very small number. This number is 0.0023. Really small. Could probably, I usually try not to write like this, be neglected. Right? That's why I type. See, now you see why I type, right? So that number is really small. We could probably ignore the projectile after it gets embedded, right? That's the point I'm trying to make. The next example we do, we will ignore it. It makes your life a lot easier because you wouldn't have to do as much kinematics when you do that, right? Because you're comparing 0.0023, the term on the left there that I've underlined is 0.0023, the one on the side there is 5/3, right? So they're not even comparable. That stuff on the left isn't gonna affect anything hardly at all, right? And so the answer here, just write down the answer and we'll go. This is omega bar equals 0.623 rads per second. That's our answer. Right. So the next one, I specifically say, hey, you can ignore the mass of the bullet after the impact because it just makes your life a lot easier. It doesn't really affect it anyway. It does have a significant effect before the collision because it's going 400 meters a second. Afterwards, it's going very slow and it has little mass at all, so it doesn't help at all. Cool, great. See you guys on Wednesday.